boys and girls. So, here's what we do. So there's a lot of ways that we can express this, but namely, what we want to do today is we want to find volume by a method called disks. And so, we'll do, 4 examples, and you guys will, be able to write down some notes, and hopefully we'll get it. Hi, all. So, yep, three-dimensional, exactly. So Brooke asked the excellent question of the day, which is how do we do three-dimensional, and I'll show you. And a lot of times people just get the formula, and then they have to ask themselves, why does it work out? So see if you can understand the reasoning behind this. If you'd be asked to find the area from A to B bounded by the function f of x in the x-axis, how would you do that? How would you find this area? Yeah. So that represents the area. And when we find the area, we add up an infinite number of rectangles, right? Now, this is so important that you follow this, okay? If I draw a rectangle, like that, do you remember, in order to find the area of a rectangle, we take the base times the height. What do we use to represent the height of that rectangle? F of x, very good. That's the height. So this part right here is f of x. What about this part right there? Yeah, dx. That's your width. Right? So all we do is we take that area of the rectangle and we do it an infinite number of times. And as we increase the number of rectangles, what happens to dx? It gets infinitesimally small, okay? Yes. So, watch what I'm going to do here. So now what I'm going to do is I'm going to take that function and I'm going to rotate it around the x-axis to make a three-dimensional shape. Now, watch this. If I want to, before we would slice and we get a rectangle. You're going to hear me use this word slice now. It's so important that you can visualize this. But I'm going to slice off the end of this. If I slice off the end of that, what shape do you get? It's close. It's not going to be an ellipse. It's going to be a circle. Well, that's because I'm drawing the end of it. Okay, when I slice something off, okay, let's say it's a ham, okay, you slice off the end of the ham, okay, all right, sure, when I slice off the ham, okay, you get this disc. Now, if you think about a quarter is technically not a not just a circle, it's actually a cylinder, isn't it? Because a cylinder is a three-dimensional figure. Instead of calling it a cylinder, we could call it a disc. I suppose we would think that a cylinder might have larger height, and a disc would simply have, maybe a smaller height. Also, a cylinder might be empty on the inside. We might think of it that way, right? Okay. Also, so if you want to find, instead of finding the area of this piece, because I want to add up an infinite number of those. Okay. But a quarter doesn't have area. A quarter has volume. Well, how do you find volume of a shape like this? Very good. So, what I'm going to do is I'm going to look at this circle right here, okay? The area of a circle area is equal to pi r squared, right? Okay, so I'll try this one time. When you draw three-dimensional figures on a two-dimensional space, they are difficult to view. Just like if we tried to look at a four-dimensional figure in a three-dimensional space, that's very hard to think of what that would look like. Okay, I could show you tomorrow if you'd like to see what a fourth-dimensional figure looks like on a two-dimensional space. Okay, we will show you that. Yes. Okay, so would everybody agree that that's the radius? Okay, what does the radius refer to, or what is it the same as? F of x. So the radius is the height of the function, and it gets rotated that constant amount all the way around. Okay, so r is equal to f of x. So if you wanted to find the area of this shape, you would say area is equal to pi times f of x squared, right? No, hold on. You're getting way ahead of ourselves. This shape does not have, it's not just two-dimensional, the shape is three-dimensional. So we need to multiply it by this, we'll call it the width. The width will eventually get infinitely small. So we're going to call the width dx. So if you can see here, we've just found the volume of this quarter type piece, or a disc. We found the volume of the disc. The disc is pi times f of x, that quantity, squared, and then we multiply by dx, and that's the volume. How many of those will we add up? An infinite number. In order to get that infinite number, we will simply run it through the integral. Nobody's gone today. So, who's gone today? Oh, hey, Cody. Sorry, buddy. All right. Well, I'm not going to say it this time because I got called out. So you go ahead.
You're not going to watch this video, Cody.
What do you think, Isaac? That's pretty cold, isn't it? I know. I agree. Cody, you are going to watch this. Cody, you're going to memorize this. Whoop. So here's the idea. This is the very big idea contained in a very small fashion. Volume is simply equal to the area times right. Sure. Good to see you, pal. There you go. He's ready. All right. So here's the big idea. Made very, very small. Are we okay? Okay, very good. The big idea of made very small is this. Volume is equal to the integral of a of x dx. What does that mean? If you ever want to find the volume, all you have to do is this. Find the area and integrate it. Time out. So, did I blow your mind? Hopefully. Okay, let's go to very practical problem. Here's a classic problem that you'll have. Again, your test will be open note. I suggest that you be, but therefore I will make it more difficult than your other tests. So I will feel free to ask any type of questions from your homework or your notes or your assignments. You have to be ready for the whole thing. The volume, find the volume of the area bounded between these three pieces, and I'm going to rotate it around the x-axis. It's so important that you start by getting a correct drawing of the shape. We have y equals the square root of x. What does that look like? Sideways parabola, the top portion, very good. It's bounded by x equals 4 and x equals 0. Well, x equals 0 is right here. X equals 4 is right here. So, we'll talk about this portion. Okay. And we're going to revolve it. We're going to rotate it around the x-axis. So, I'm going to draw that same type of shape. And what I like to do then is I like to draw kind of the end of it to show that disc piece. What are you talking about? You want a hole in the middle? So, as long as we can find our big idea today is that all we got to do is find the area of a slice and integrate it, and then we have volume. So it's as easy as that. So let's take a slice. When you slice it, what do you get? And that's what we'll get today. You're not going to get that all the time. Okay. This is really, really, really important, okay? Because we're going to pick up with this later. It's not going to change today. Today I'm going to keep them all simple. But I love to do this. Okay? Because the radius is going to be the top part minus the bottom part, right? What is this middle part right here? What is this line? What is this x-axis, also written as y is equal to 0, right? And then this top portion up here, what creates the top part of your disk? Y equals the square root of x. Very good. And does everybody agree that the distance between the square root of x and 0 is just going to be whatever the square root of x is? I don't always have to rotate it around the x-axis. Sometimes I can rotate it around, say, y equals -1, or y equals +1, or I could rotate it around another type of line. So this distance is important to keep in mind, and that's how I always make my drawing. we have a shape that is a disk. I know I need to find the area of this by simply doing pi r squared. Area equals pi r squared. So area is equal to pi times what is my radius? Yep, this is my r value, which you stated is the square root of x. So the square root of x, that quantity squared. So area is equal to pi x. What is the width? Dx. So the volume of this piece is pi x dx. We're going to do an infinite number of these. If we're going to do an infinite number, we need an integral. What is our, where are we starting to integrate from? 0 to 4. And we have the integral. I like to write my pi out front. X dx. Yep, so all we're going to do here is increase the exponent by 1 just like you did before. We have our pi, and we're going to have x squared over 2 evaluated 0 to 4. Plug in 4, we get 16 over 2 or 8 pi. So that looks like a very ridiculous thing to take that shape and try to find the area or the volume of it. We did it very quickly. Yes, that's the volume rotated around the x-axis. Zach? It's both halves. Because if we wanted to state the area of just the top half, the circle formula would have been 1/2 pi r squared. Whatever, and so that's a great point, Zach. If you wanted to just do a top half, you could state the area of a semicircle instead. It's the same way. Okay. Let's try another one. Volume bounded by y equals x squared plus 1 and x equals 0 and x equals 2 rotated around the x-axis. Draw my shape. What does x squared plus 1 look like? The parabola shifted up 1 unit. I want you to be very, very careful because right now I'm focusing on area and volume that is represented, I should say area that's represented in the first quadrant. But we can be given problems where we do go over the second quadrant. Now, is it symmetrical about the y or y-axis? Yes, it is. And so since it's symmetrical about the y-axis, you could simply go to 0 and double it. But we're not doing that. It says you're bounding from x equals 0. So x equals 0 is here, and x equals 2 is there, and it's going to be rotated around the x-axis. Well, if it's rotated around the x-axis, I'm going to have the same type of shape drawn below. In order to give it its three-dimensional shape, I like to just kind of draw the circles in there. Yep. So this is like a, maybe like a stand that you would set a plant on or something. It's solid all the way through, right? When we slice it, we do get a disc shape. What's the width of our disc? Dx. So we want to integrate an infinite number of these, so I need the volume of this disk. In order to get the volume of this disk, I need the area of the top part. Again, what's traveling through the middle is y equals 0, and the top is what provides the height for me. What is the top? Y equals x squared plus 1. Yes. Only because last time, if you notice right here, it came to a point. And this time it didn't come to just a point, so I drew a circle on the back. You sure wouldn't have to do that. I'm just trying to... You could use this circle and as well if you wanted to. Either way, it doesn't matter. The point is that you do get a circle shape. You do get this disc. If you're to slice it on the back or the front, you get a disc. So I need to find the area. We know the width is dx, so the area is going to be pi r squared. My radius is x squared plus 1. So the area is equal to pi times x squared plus 1, that quantity squared. How do I do that? Yeah, so the area is equal to pi times x to the fourth plus 2x squared plus 1. And so the volume then is when I take that multiplied by dx. And we want to do an infinite number of those. So I use my integral. What are my bounds? 0 to 2. And I'm going to go, let's see, pi out in front. And we've got x to the fourth plus 2x squared plus 1 dx. So on your test, I'll be asking you to set up your definite integral correctly. We all know how to evaluate a definite integral, don't we? We've done that many times. Now you understand why we practice it so much. But now we need to actually go about this and evaluate it. So this is extra algebra practice with the antiderivative of x to the fourth. X to the fifth over 5 plus there we are. 5 and 3, what's going to be my common denominator? 15, so I'll create everything in 15ths. What is 2 to the 5th? 32 over 5, otherwise known as 96 over 15. Plus 2 to the 3rd times 2. 16 over 3, otherwise known as 80 over 15. Plus just 2, or 30 over 15. And then we subtract 0 off, which gives us whatever we have here. So 96 plus 80 is 176, plus 30 is 206. Is 206 divisible by 5? Is it divisible by 3? Do you know how you can tell? 2 plus 0 plus 6 is 8. That's not divisible by 3, so 206 is not divisible by 3. That works for 3 and 9. You try example 3 on your own. Any questions? Any concerns? The back. Okay, so everybody, Megan asks an excellent question. In fact, I think Bailey asked it before. It was about the backside. I want you to understand here, we did find the area of the backside. What happened was we took and we integrated from 0 to 4. So it starts at this 4 piece and it pushes it all the way back to 0. So we've done every single disk between 0 and 4. So this back one has been accounted for because of our bound. Okay, last example. Find the volume of the area bounded by the curves negative x squared plus 3x, x equals 0, x equals 3, rotated around the x-axis. If you look at this curve right here, negative x, if we factor out a negative x, we get x minus 3. So where does that thing cross the x-axis? 0 and 3, yeah. So you've got this parabola shape here, and is it right side up or upside down? It's upside down, so you know you kind of got that shape going on. And so I can draw the same thing right there. And, you know, you may not like that because it's like, well, how do I get a three-dimensional drawing off of that? Well, just slice it. If you want to get a good shape, are you going to slice it at the ends or are you going to slice it in the middle? So slice it in the middle. If you slice it, if you take, you know, just, you know, something really small right out of the middle, you know, that's what you get, right? So that's what we want to find the area of. We find the area of that shape, and we can integrate it. So again, that makes our classic disk shape that we've been working with. We're centered around y equals 0. What makes the top part? Negative x squared plus 3x. So the distance between negative x squared plus 3x and y equals 0 is just the, you know, whatever negative x squared plus 3x is. So area is equal to pi times your radius, negative x squared plus 3x. We're going to square that. And then we know that our width of this shape was our dx. So all parts of the integral are accounted for. I'm not trying to do that. So I'm going to integrate, what are my bounds? 0 to 3, that's where it crossed the x-axis, and it tells me up there 0 to 3. Just kind of helps confirm my drawing here as well. I'm going to square that out, and I get x to the 4th. And then I'm going to get a negative 3x to the 3rd, and then I'll double that to get negative 6x to the 3rd. And then 3x times 3x will give me 9x squared dx. So that's my integral. So on the test, I give you a point for the drawing. I give you 2 points for the integral set up correctly, and then I give you a point for your final answer. All right, let's integrate. Pi times x to the 5th over 5 minus 6x to the 4th over 4. Could reduce that to 3/2 plus 9x to the 3rd over 3, or just 3x to the 3rd, evaluated 0 to 3. What's my common denominator? 10. What's 3 to the 5th? 243 doubled, and I get 46 over 10 minus 3 to the 4th. 81 times 3 is at 243. And we got multiplied by 5 to create common denominators. 243 times 1250. 1215 plus then 3 to the 3rd is 27 times 3 is 81, and then we're going to multiply that by 10. 810 over 10. So we have our common denominator of 10. What is 486 minus 1215 plus 810? 81 pi over 10. I will take points off if you do forget the pi in your final answer. Here's what I want you to start on. We are going to work tomorrow in class, but here are 4 problems to get started. 6.2, page 391, numbers 1 through 4. Yep, I would like you, I'll take questions on some of the beginning of class, but I would rather that you come knowing if you could do 1 and 2 but not 3, or if you can't do any of them, or if you could do all of them. That'll be much more helpful to me than if we just said, okay, we're going to take, 20 minutes to work. Okay, so see what you can do, see what you can't.